We would like to present to your attention a new universal approach to lifetime management of simple and complex technical objects. Resource Expert Mubatec, REM, a multiparametric online monitoring concept for assessment of long-lived critical systems, structures and components, SSCs, with time-limited aging to justify the additional years of safe operation. REM, as an advanced lifetime prediction methodology, has been created in order to justify the extension of usage of nuclear power plants beyond their designed lifetime. Usage of REM for controlling the equipment, buildings and structures of nuclear power plants could substantially reduce the risk of damage and destruction. Our multi-purpose approach allows to securely identify weak areas based on calculated and experimental analysis of the actual loading, look into the future and estimate exact residual resource of the whole construction and each unit separately, estimate how to change level of operational damage of construction without compromising its reliability and efficiency, predict time and define cause of failures, organize online monitoring of actual loading and survivability of construction even beyond original design lifetime, optimize in-service life inspection, maintenance of SSCs, and maintain a high level of safety. For better understanding of the main idea of REM, let's consider the traditional approach to crane life management for long-term operation. Many different mechanical failure modes exist in all fields of engineering. Traditional approaches use idealized model of construction based on previously implemented stress-strain calculation. Such approach does not take into account the factual aging level of material and the factual thermoforce load, but long-term operation changes the mechanical properties, initiates and grows cracks and defects in the base metal and the welded joints. All these can be determined by test of specimens in the laboratory. Mechanical testing is a very useful step for failure analysis. To introduce the concept of loading and fracture, it is useful to examine the simple tensile test. This provides a definition of the common tensile mechanical properties, and these properties can often be estimated from hardness measurements. Hardness is a simple test to perform. Aging reduces fatigue resistance, cyclic strength of the material, or the number of cycles to failure n with the selected applied stress amplitude sigma max in cycle. Thus, the number of cycles to failure delta n dramatically decreases. Main failure mode is failure due to fatigue, that is, from repeated loading. Aging reduces fatigue resistance. The time of number of cycles n to reach fracture increases with a reduction in the magnitude of the stress amplitude sigma max in cycle. The fatigue life, n, is a number of cycle of stress or strain of a specified character that a given specimen sustains before failure. Failure for exactly n cycles can be determined from SN diagram. Aging reduces the static and cyclic crack resistance of material. Ductile to brittle transition behavior of fracture toughness, KIC, decrease in temperature. To compensate for the degradation process and secure our ignorance of the actual susceptible materials and components to loading, a safety factor N is used. The safety factor gave rise to conservatism in stress-strain design. Used coefficient of a margin of safety factor N has led to high conservatism in the estimation of the real condition assessment of aged structures. However, even if the coefficient N greatly exceeds 1, it is not a guarantee of safe operation, because for stress-strain design, use only exclusively the design scenario of loading and also minimal level of mechanical properties. Resource expert methodology is free from such limitations. It uses only actual configuration and real mechanical properties for stress-strain design. It takes into account only real measures of loading and damaging considerations from online monitoring data. And it also uses the verified finite element diagnostic routine of stress-strain design. Let's assess the main principles of resource expert methodology applied to universal laboratory full-scale model of power plants. Now, nuclear power plants are one of the most complex technical constructions. Units of NPP include more than 25,000 of components having the same technical solutions as the most standard technical facilities and consisting of similar assemblies, pressure vessels, pumps, pipelines, flanges, nozzles. Of these elements, the designer creates a design basis sketch of the primary object. Designer uses these elements for design work basis sketch of construction and selects design parameters, dimensions, calculating wall thickness, material grade, maximum operating pressure and flow conditions, operating temperature, pressure drop, corrosion protection, support for metal and concrete. On the basis of the sketch, the final design documentation is developed. Design documentation applies for manufacturing of construction. During the operation, the equipment is exposed to various stresses: internal injury attacks, temperature, external forces, static and cyclic loads, vibration, emergency dynamic and static loading, wearing, corrosion. All mechanical equipment failures fall into these general categories of influence. The failure management process consists of three basic parts. Part 1. Selection of safety important systems, structures or components for which aging should be evaluated. Part 2. Understanding of dominant aging mechanisms in selected components and identifying or developing effective and practical methods for monitoring and mitigating aging of the components. Part 3. Managing the aging degradation in selected critical components by effective practice and approaches in operations. Our methodology of aging management uses the new approach of online process and components condition monitoring and diagnosing. The first step in the implementation of the resource expert approach is, as well as in the traditional approaches, a collection of design and technical documentation, such as design documentation, data on the operating conditions, and the history of defects, rupture, and repairs. The design documentation can differ from actual design geometry. In the resource expert approach, in order to compensate for this, a 3D laser scanning location is used as volume control that clarifies the actual geometry with all the features and deviations from the project. And also, a random non-destructive testing of defects and mechanical properties is implemented. According to the actual geometry data, a finite element model is run in our special software FEM Expert Mubatec. Numeric FEM model is a simulator of actual operation. Learning ability of the FEM model is our know-how, which makes it possible to quickly improve the quality of calculation based on iterative algorithm on the received design data from online monitoring. The first FEM calculation uses the design documentation and operation conditions data. We determine the areas of construction requiring special attention. On these parts of construction, the sensors will be installed. Our second know-how lets accurately determine where, how, and which sensors to install, monitoring for further success training finite element model. Unified Autonomous Monitoring Unit is a key element for implementation of online condition monitoring. Sensors are connected to the unit used for general information about the monitoring process. This process information is then collected and communicated to the data analysis system by the data collection system. The next stage of condition monitoring work is performed on the object itself with our specialists, experts in non-destructive testing of facilities. In critical areas, the necessary sensors are mounted and data collection channel is organized for collecting, storing, and transmitting data. The sensors are resistant to any aggressions of the environment, and all information collected may be continuously transmitted anywhere in the world in online mode. Now, depending on the complexity of the object, different phase-time data collection and training modes of our finite element model are possible. The process of collection and transmission of data is not tied to place and the people, and this is one of our know-hows. Finite element calculation model is self-learning. The model is trained in the online mode until the data from its calculations matches the real data derived from the monitoring unit. Calibration and training of the finite element model is performed by means of comparing of the calculation data at the control zone and of the experimental data of deformations, displacements, and temperatures in different operational modes at different loading levels of the monitored object. As a result, we have a real scenario operational loading facility and trained finite element model. By combining them, we get a time machine, learning-based computational experimental model that could see the state of the equipment in the future as well as in the past. Having laid the scenario in our intelligent FE model to identify the previously weak link of our equipment and having performed the calculations, we are now able to evaluate how the equipment will behave after a certain period of time, as well as to calculate the total damage cumulative since the start of the object in operation. For the most accurate estimations to assess the real safety margin and the determination of survivability of the material in the most loaded areas of the equipment, we use the method of direct physical modeling based on laboratory tests of full-scale test patterns which imitate these areas. History of thermopower loading of laboratory test patterns is formed from the results of a numerical calculation based on the actual data received by resource expert system. Testing of the pattern is carried out on servo hydraulic testing system MTS Landmark, equipped with a system of rigid attachment of the model to the frame of the machine. Additional control systems of model loading consist of 4 sensors, strain, timing and displacement sensors that are also connected to the MTS machine. All sensors are synchronized with the central system controller MTS Landmark over Wi-Fi via MTS Echo software. Outside the defined environment, all load models are carried out loading device MTS Landmark. Data from additional sensors monitoring system allows the model to predict the behavior of the material in the critical zone. Application of the full-scale patterns has allowed to define the basic dominant mechanisms of failure and the actual time to failure without conservative components such as the coefficients of safety margin. The equipment is often subject to cyclic stress variations. These variations can cause defects and failures at stress levels lower than the yield strength for static loads. When conducting fatigue calculations, there are two main approaches: the SN curves approach and the fracture mechanics approach. First, the SN approach uses the curve of different stress levels until failure occurs. This SN approach is generally used at the design stage for equipment. The remaining fatigue life of a crack can be calculated using fracture mechanics by using Paris equation and sigmoidal fatigue crack growth diagram. Work on optimizing of the cost of operation by using the trained FEM model for calculating the different loading parameters to simulate their effect on the performance of the equipment and the actual decrease of failure due to the introduction of compensatory measures. The implementation of compensatory measures consists of setting of the acoustic emission integrity monitoring system to the danger zone and of smart ultrasonic control system in critical areas of equipment, and changing the particular design solutions such as strengthening of the subsystem elements, etc. Then an online non-destructive monitoring allows to improve the numerical calculation analysis by obtaining data on detected defects both outside and inside the equipment. All these 10 steps are resource expert Mubatec itself. Lifetime management characteristics of controlled equipment on the basis of multi-parameter calculation experimental methodology. While using it, we move to a new level, allowing the maximum objective assessment of current condition and residual life of key components and structures based on previously gathered data and offering compensatory measures to improve survivability of the object. The objective data about nodes and areas prone to the highest operating loads and data on the causes of breakdowns, the possibility of preventing them in the future based on the results of only computer simulation of the last period of operation.